to the next page. The imperfect information in games such as like pokers have large data and action spaces. So I think that reinforcement learning is very fit to slow the poker game's progress. Next page. First, we introduced the CFR, and this is the flow chart. First, we build an information set, represent a set of game states, and which don't have perfect information, and all calculations in CFR are based on these information sets. And then we calculate the players is paid at utility at the information set I on the policy sigma. Next page. And then we calculate the regret. And the regret means the protection difference in utilite from not choosing in attention A, and the positive regret means that choosing action A could have a higher utilite, and then at each iteration we add the current regret to the accumulated regret. and then we use the accumulate regret to update the future price. Next page.
Okay.
Science.
Now I will introduce the basic Q-learning. Q-learning is a model free of policy reinforcement learning algorithms, and its object is to maximize its action value function. Next page, please. Next page. DQN is a method that combines neural network with Q-learning, because Q-learning suffers from the simultaneously present of the data threads, and so it can't guarantee coverages and can even become unstable. To address this, DQN aid two key mechanisms compared to Q-learning. First mechanisms is experience replay. Experience replay allow DQN to learn from stored past transition by randomly sample mini bench. During training, we break up data for correlations and improve sample efficiency. And the second mechanism is target network, a separate network whose parameters are copied from the learning network, but not every step, few step one time. And this provide a more stable target for the TD update and reduce the instability in the network training. And next page, please. And because the DQN is off policy algorithm, so we can learn from data generated by external policies. Therefore, we introduced CFR. After training CFR offline, we import its result into DQN as an offline dataset to aid DQN training. And this can be seen as a simplified Rebel workflow. We avoid the repeat training between the network and the CFR. We just simply training CFR, generate the data set, and train DQN. And its advantage is, and its advantage is, in part, is relatively straightforward, and it can be developed independently, but its coverage of application is limited and it's difficult to update.
Let's introduce how the DQN algorithm is applied in blackjack. I'll start with the game rules. The rules is presented in this page. I will just skip it. Here's how the rewards in this game is defined. The +1 reward for winning, -1 reward for losing the game, and 0 reward for drawing. Here's how the state and action space is defined. There's 2 dimension for the input and output space. In the neural network we define, there's also 2 hidden layers. Each layer has 64 nodes. Let's talk about the logs function. We trained the agent using the Bellman equation to update Q values. There's 2 set of parameter are used. The online Q value update every episode. The target network updated 1,000 training steps. Is the logs function is defined as the true the estimate Q value minus the Q value from Bellman equation. Their square sum. Here's the inadequacy of our application. We don't have too much state space for the input. We have only 2 dimensions of the input. We could have done more. Here's the result of our DQN application. Here's the plot with a reward across episode. We could see that the DQN with deterministic decision and DQN with softmax is have the same performance generally. Here's the we have also generated the policy table where the optimal action for each player sum and dealer card is presented. We could see the optimal action for each state. We have also loaded 4 agents to let them engage in the blackjack game, compare the win rates in 10,000 games. We have come to the conclusion of DQN greedy have a better performance than DQN softmax and much greater than the random decision.
Okay, let me introduce how we define the game state and implement CFR in our project. We are dealing with Lederhold'em, which is an imperfect information game. That means players only see partial information, like their own card and the action history. At the top left, you can see the state space definition. Each state includes the private hand, the public card, and the history of actions. At any state, the players can choose between flawed, call, check, or risk, or scared risk. Depending on the great game context. On the right side of the slide, we show 2 flowcharts. On the top one describes the training loop. It starts by resetting the environment, initializing strategy probabilities, and then develop the game tree for each player. After each round, it updates regrets and the average policy. Below that, the second diagram shows the CFR works. If the game is over, we return the payoff. Next, here we show the training results of our CFR agent. Let's first look at the 2 reward curves on the top. This shows how the agent improves over time. On the left, you can see a sharp jump in the performance in the first 1,000 episodes. then it's gradually stabilized around 0.75 to 0.85. On the right, we zoom into another run that trained for 5,000 episodes. Even though there's some variations, the trained stays above 0.7, which is a strong sign of learning. Now, if we look at the table at the bottom, it shows the agent's learned action probabilities for different private hands. For example, with SK, the agent choose to check with 94% of chance, and for SJ, it prefers to float. This table tells us the agent is learning very specific strategies depending on its hand. Next, this slide shows key results from our evaluation. On the left, you can see a win rate comparison. Our CFR agent won about 66.74% of the game. This confirms that our agent has learned a strong strategy and consistently beats random opponents. On the right, we show an example of a game between the CFR agent and a human player. In this round, the human holds a queen and the CFR holds a jack. Here, the human chooses to float. The CFR chooses the same. This shows that the CFR agent is not blindly aggressive. It chooses actions carefully based on the situation and the history of betting. Next, in the final slide, we show how our implementation follows the CFR design described in the recursive belief-based learning paper, and how we understand its potential for extension. On the left, we highlight several key parts that we focused on in our implementations. We implemented trees traversal and average policy updates, which are core parts of the CFR module in Rebel. We use information set-based abstraction to represent decision points on the imperfect information. And we also enabled strategy exports so policies can be saved and reused in the future modules. On the right side, the diagram shows this fits into the Rebel framework. Our current CFR agent provides a strong offline foundation. Based on this, we can extend the framework by integrating in reinforcement learning solvers like DQN or PPO to optimize subgames. So that's all for our presentation. Thank you.